Thank you very much for the warm welcome. Thank you to all for tuning up today. Really appreciate it, especially in these trying times. I see a few faces or a few names come up to recognise. I hope you're all well. Just to start off a little bit about Grundfos, this is the only part of the presentation where I talk about Grundfos as such, but we're a global company, private company, family owned. So 85% of the Grundfos global turnover goes back into the company, into R&D, and to the various offices, workshops, manufacturing and assembly plants around the world. That's our little plant down in Christchurch where we test and assemble pumps, over 250 kilowatt. Every pump is tested prior to leaving the factory. Today, I'd like to cover 5 topics, and this is really just, it's an overview of each topic. Topic 2 and 5 are probably the most, not critical, but probably really important 2 areas to cover that we'll do today. If we look at centrifugal pumps, we've got centrifugal pumps, and we also have displacement pumps. For us, most of our pumps really are centrifugal type pumps, single stage and multi-stage. And the principle behind the pump is to take the water into the suction port and deliver it out through the discharge. So the pump is entering in and out through the discharge point. And the motor driving on the other end, depending whether it's a 2-pole or a 4-pole, will depend on the head that the pump can actually produce. So the 1450 or 4-pole motor will produce a lower head than the 2-pole. If we look at the types of centrifugal pumps that we see in the bulk of our systems today, we have the single stage pumps, both end suction and single stage and inline. We also have a range of multi-stage pumps. The multi-stage pumps came out in the late 70s. Prior to that, single-stage pumps had to be generally big pumps, big base-mounted, big impellers to create a high head. Now we use multi-stage pumps, and using a multi-stage pump, we can take up a much smaller floor space and become a lot more efficient. The impeller curve, we'll have a look at this a bit later on, but the impeller curve for a single stage pump is quite flat compared to a multi-stage pump. And if you look at the vertical multi-stage pump, second to the right there, the water enters into the inlet flange, it goes up to the first impeller, it then forces water into the second impeller and on into the third impeller. Each time it does that, it doubles its head as it goes through. The curve is very, very steep and makes it ideal for pressure systems where you're trying to drive variable flow and maintaining a constant pressure. You can move from one point on the curve at a high flow rate and then reduce the speed of the pump to the left-hand side of the curve, and there's a huge variance in the shape of the curve for that pressure. If you have a flat curve, it's very hard to control on pressure. When you move from a high flow area to a low flow area, you can change a great volume area, but the pressure doesn't change a great deal. The guy on the right is a water-cooled submersible pump, and that is what we see sitting in the bore, and that could be 300-400 meters in the ground. The bottom part of the pump is the motor, and that really relies on water passing across the motor into the intake. There's a screen just above the motor, and the water goes through the screen into the first impeller, and then it moves on up the impellers to the discharge. At the top of the pump, there's a non-return. Some of the areas or the considerations that we need to consider when we're designing our systems, and to give some thought about, is the pump types, whether we go inline or end suction, close coupled or long coupled, just depending on the configuration of the pipework. The pump housing, the impeller material. If it's a closed loop system, heating and cooling, then cast iron impellers are fine. But whereas for cooling tower, domestic hot water, we must use a a stainless steel or a bronze impeller, just to avoid any corrosion in the water. Then the motor variants, just depending what we're looking for there, if you wanted to go to a fixed speed motor or a variable speed motor. And then the communication. And today, I guess the delivery is a hot topic. It's getting our deliveries coming in out of the factories vary greatly. So please, if you're considering some deliveries on pumps, really give that a little bit of thought. The last thing is to let you down on that. Can be as long as the chiller. The big consideration for any systems that we look at is the life cycle costs. The initial outlay of the pump is only 15%. The total ownership of that pump, so if you own that pump for 15 to 20 years, the energy cost is the greater part by far. And I guess if we can have a look at that at the early part when we're selecting our pumps, take that into consideration. If you think about an irrigation system or a farm system, and if you consider the cost of running the pipe work, comparing, for example, a 32mm pipe and a 65mm pipe, you might find that the 32mm pipe needs a 7.5 kilowatt motor to drive the flow through the pipe work, whereas if you use a larger pipe, then we can cut the motor size down, and over that 15 to 20 years, the energy costs will pay back what it cost you initially for the change in pipe size. Moving on to the pump performance curve. The pump performance curve is data that the manufacturer produces, and the performance curve indicates how we get to the performance curve is by the diameter of the impeller and the motor speed. And in this particular case, in the blue line here, I'm just trying to get my pointer to go, but it won't just work. Bear with me 2 seconds. No, it won't work. The blue curve is the performance curve, and if you follow that, you can see at the top left-hand side it reaches 50 meters, and out to the right-hand side it drops down to about 35 meters. The performance curve is what we expect the pump to work to, depending on the flow rate. And if we have a look at a flow rate of 70 litres a second, and we take that vertically up, where it hits the performance curve, we go horizontally across, and we can see that pump will produce about 42 meters head. The performance curve is a promise by the manufacturer that that pump will actually meet that curve, and each pump is tested to that pump curve prior to being dispatched. There is a tolerance around that curve, so as long as the guys that are assembling and testing the pump meet that tolerance curve, then the pump can go out. We can't get off that performance curve. If it's a fixed speed pump, we have to stay on that performance curve. And it's relative. I guess the best way of looking at it is, if you imagine you've got a hose without a nozzle on the end of it, and you're trying to get water to one end of the garden, and you can't get it down there. What do? You put your thumb over the end of the hose, and all of a sudden you get the water to the other end of the garden. What you're doing is you're reducing the flow, but you're increasing the head. So at 70 litres a second, you take your thumb off. If you put your thumb on the end of the hose, then you'll increase the pressure, but you'll reduce the flow rate. The efficiency curve, the black moon-shaped arc there, that is the hydraulic efficiency curve. So that's indicating where the pump likes to run. And what we call a best efficiency point, the BEP, is always up at the peak. And the peak of this one, is around about 60 litres a second. If you have a look at 60 litres a second, and where it meets the BEP, the best efficiency line, we take our eye to the right, and that then gives us our efficiency. So this guy here at 60 litres a second, the best efficiency for that is about 72%. If you are concerned about minimum flow, the last thing you want to do is run that pump against what we call a closed head for long periods. A closed head is zero flow. If you shut the valve off, the pump would be running at zero flow, and it would produce around about 50 meters head. And that's a really good test if you want to see if a pump is actually working correctly, if it's running in the right direction, or to be sure that there's no issues with the impeller. If you shut the discharge valve, the gauge should read about 50 meters head, then you know that that pump is working. Minimum flow is always around about 10% of the best efficiency, and that's based on cold water. So in this particular case, minimum flow would be around about 6 litres a second. If the water temperature is higher, I always allow a little bit more, just to give you a bit of safety, because you don't want heat building up inside the pump housing. Next to is the power curve, and you can see in the box just below, we now have 2 more curves, and we've got the power consumption curve, and that's relative to flow. As we increase the flow rate, we obviously increase the power. The performance curve is what we call full non-overloading. So that means the motor that is fitted to that pump will follow the complete pump performance curve, and it won't overload. Years ago, we used to have pump performance curves which would have splits along the pump curve, and they would be indicated with kilowatt ratings. So the left-hand side of the pump curve, it might have had a 7.5 kilowatt, then a little further down the curve, it might have had another 11 kilowatt, 15, and then 18.5 at the end of the curve. And that meant that wherever you sat that pump on that curve, that was the motor that you needed. These days, we have one motor fitting that whole entire pump curve, and then you shouldn't overload. I put this in. This is really quite good. The pump head, and some of us get confused, especially if we're learning. 2 systems. We've got an open system and you've got a closed system. In an open system, and it may be pressure boosting. We're boosting water from the basement to the top of the building. In that particular case, we have to measure the height of the static height, and all the losses in the pipework and all the fittings. So that's an open system. In a closed loop system, where it could be chilled water or heating, we don't have to consider the height of the building when we're calculating our head for the pump. All we need to do is calculate the losses through the pipework and through the fittings and any units that we're putting water through. I guess that's the easiest way is to look at it as like a bike tube full of water. And while that water's sitting in the bike tube, it's pressurized in the bike tube, but we need to move that water around. So when we move the water, we incur some friction, and that's resistance, and that's what the pump needs to overcome. So in an open system, 10-story building, we're pumping water through into showers to taps. We need to measure the height of the building, the losses through the pipework, and the losses through all the fittings. Whereas if it's a heating system or a chill water system in a 10-story building, all we need to do is overcome the losses in the pipework, the fittings, and the units that we're connecting to. If we look at the water supplies and we're having to calculate our head, then if the water is below the pump, we have our static head now is from the water level where we're pulling water from, straight up to wherever we're delivering the water. So on the left-hand side, the picture on the left-hand side, we've got a suction lift, and then we have a static head. It's the total of those 2 guys, plus the losses in the pipework to give us our head. When we have a flooded suction, we take the level of the water above the pump, and then that's the start point to the delivery point is where we're trying to push it into. Just one thing to note, when you have a submersible borehole pump sitting in a well, you might have the pump sitting at 200 meters down the well, and when the well driller comes along, he'll generate the given flow that we're looking for. So he'll purge the well. The water table might be sitting at 5 meters below the ground, but when he pumps it down, So he generates the flow rate that we're looking for. He might pull it down to 100 meters. So at 20 liters a second, that water is drawn down to 100 meters, but we've got our pump sitting at 200 meters. We only need to start our suction lift from where the well is drawn down to at the 100 mark, not 200 meters. If we start at the 200 meters, we've just oversized our pump hugely, and that's a lot of energy, plus also over-pressurizing. We don't need to over-pressurize the system. So always take it from where the water level is to the delivery point. If we look at our efficiency curve and our best efficiency and our pump curve, this is a really good graph to indicate what's actually happening inside the pump. And this is why we try to always select the pump around its better efficiency area. And good practice, or better practice is minus 20 to plus 10% in and above the best efficiency area. It's not always possible. Sometimes we get stuck. We end up having to select a pump sitting in another part of the curve, higher up or further down. But this is a really good guideline. As you can see at the top end of the performance curve, we start to generate high temperature, a little bit of cavitation, a low bearing, a low loading on the bearings. You're also going to get a lot of noise up that top end there, especially if you've got a big pump trying to punch a lot of water out. It will become really, really noisy. All of that will tend to end up increasing the service life, reducing the lifespan of the pump. And then we go out the other end, we start to get loading on the bearings again. We get a little noise, and then we run into cavitation. And if anybody's heard cavitation, I'm sure some of you have, it sounds like gravel going through the pump. And cavitation, if we leave it long enough, it can really start to cause some issues. We get mechanical seals failing, we get motor bearings failing, and a number of other bits and pieces, which is just weakening the pump. And it's going to cost money. At the same time, it's costing a lot of energy to drive it in those areas. This is a couple of shots here. You can see the one on the left is cavitation. We'll talk about cavitation soon. And that's the suction port of the impeller. And you can see what's left of the vanes. The cavitation has drilled into those impeller vanes and really destroyed it. That's how much is happening inside that pump. There's so much turbulence going on when it's cavitating. The one on the right is the back end of a pump housing. That possibly, there's a lot of erosion going on there, and you will see that if the pump is running in its best efficiency point, and then all of a sudden it shifts out to the right-hand end of the curve. A typical case of that would be like a swimming pool. You're running the pump, which is circulating water around the pool, and then you flick it over to a back flush, and under a black flush, then the head's different. The head's a lot lower, and all of a sudden the pump will just shift straight off the end of the curve. Now that pump housing is probably 10 mils, 12 mils thick, and I've actually seen jets of water coming up the back of some pump housings caused by erosion. The one in the middle, I took a photo of that. I thought that was quite good. That's a mechanical seal leaking. When I went into the plant room, they had a yellow coat over the top to stop the water getting out all around the plant room, and there was a mechanical seal leaking away. So the best way they thought to fix that was cover it up. That's not a good one. If we're running our pumps in series, the effect on the performance curve now is we get no real change in flow rate, but we double the head. And again, this is our multi-stage pump. Where we talk about the multi-stage pump, every time we push water from one impeller to the next, we double the head on the way up. If we took two pumps now, the same size pumps, and put them in parallel, we have a common suction feeding two pumps and a common discharge. We now double the flow rate, but the head stays basically the same. If we have too higher friction loss in the discharge when you run two pumps, then you may not double the flow rate, but in general that's what will happen, is you'll double the flow rate. This is why we use booster pumps. Always remember, put a non-return on each pump. If we don't have a non-return after the pump, one pump can then poke water back down into the head of the other one, and then we have a problem. One other thing to consider when we're talking about the pump head is if we're pumping products that aren't water at 20 degrees. All pump performance curves are designed for water at 20 degrees. If we change the water, if we're pumping glycols, then the density of the water will change, and that will then impact on the performance of the pump. The pump will still produce flow and it'll still produce pressure, but it might not necessarily give you what you think you're going to get. So in other words, if you look at the second guy in here, we've got a little pump sitting there above the water, and it's 20 degree water, and the density is about 1000. That pressure gauge is reading 1 bar. If we climbed up a ladder, up a vertical pipe, you'd find that the water would be sitting at about 10.2 meters. Now, if I compare that with brine, I'm pumping brine now, the one beside it on the left-hand side, the pink one. The gauge is still reading 1 bar at the pump, but now I'm only producing 7.3 meters. Because if you have a look at the density, it's now 1.3. It's moved. The water's so much heavier, the pump is just unable to produce the pressure that we expected for a normal performance curve at 20 degrees. So always just consider, if you're pumping glycols, what effect it's going to have. If you're pumping propylene glycol, ethylene glycol, in a reasonable percentage, 30%, and it's getting down in temperature, it will impact on the performance curve, it'll impact on the power curve, and the efficiency. If you have to select a pump to pump a product which is a lot cooler than water and denser, and you know that you can't do anything about it, you're stuck with that same pump, keep the pump sitting high up on the curve, at least to the middle of the curve. That way you won't overload the motor. If you get somebody called you up and say, look, my pump keeps overloading, it might be a vineyard, for example, and the pump's running out towards the right-hand end of the curve. What's happened is, it's because the product's so much denser, you've just taken up all the extra motor power, and it can't do it, it'll overload. The positive suction head, it can be easy to understand, it can be really tough to understand. But if, as I mentioned, Danglish, which is Danish, hopefully in the next couple of slides, this will make life a bit easier for you, and we should be able to hopefully understand it. Pumps don't suck water. I remember years ago going on site and the engineer standing there, the fitter, the engineer, and he said, oh, I can't get your pumps to run. They're bloody hopeless. Can't get them to run. And the pump's beautiful big booster set sitting there, and it's pumping water into the council main. It's pulling water from below the ground. And I just happened to walk past the diaphragm tank, and it was light. It was as loose as anything. And I said to him, there's got no water in the diaphragm tank. And he said, no. And he said, should it? I said, yeah. Is it primed? He said, no. He said, the pump will pull the water. It'll suck it up. Pumps don't suck. No, a centrifugal pump will not suck. It's got to be filled up with water. It's got to be primed. So you need to, in this particular case here, this pump is pumping from water below the ground. It has a foot valve in the tank, and then we fill the water from the pump all the way back down to the foot valve, and then we bleed it. We get the pump to work by atmospheric pressure. So the pump, even though it's full of water and it's primed, it just won't pull the water. Atmospheric pressure, which is holding all of us down, is actually pressurizing onto the water. The atmospheric pressure, or the value of that, must be great enough to overcome the losses in the foot valve, the pipe work, the static height, and anything else between the water and the pump intake. And then the pump will work quite happily. Oh, something's gone astray with the screen. I've lost, oh no, sorry, come back, got it. So looking at cavitation and how it actually happens, as I mentioned, when the water is in the pipework and it's leading up to the intake of the pump, atmospheric pressure is pushing that water pushing onto the surface, forcing the water through the non-return valve, up the pipe and into the pump. Where cavitation works is right at the intake of the pump at the impeller vanes. When the water enters into the pump, as long as there's enough pressure to actually get into the pump and then overcome the net positive suction head requirement for the pump, it'll work. If we haven't got enough atmospheric pressure when it enters into the impeller eye to overcome the resistance of that impeller, that's when the water will turn to a vapor. So looking at that little chart at the bottom here, you can follow it down. We've got at A, we've got pressure. At B, we've got some friction loss. We're losing some pressure. At C, we're now losing more pressure due to the pipe work and what have you. As we get to D, all of a sudden, our atmospheric pressure is unable to overcome the net positive suction head required for the pump. And at that point is when it starts to vaporize, and that's cavitation. When the water's leading up slightly into the impeller vane, it's just starting to move up into the vane. Some of that vapor and water mixture is starting to create some pressure. So as it climbs up the impeller vane, that mixture condenses back down to water. And so that in that passage between D and E is where the cavitation is happening. That whole area is expanding 1,600 times and then contracting back down again. So you can now understand why the impellers take such a hiding. When there's all this cavitation happening within that impeller around those vanes, it's stressing the whole pump. The impeller's getting a hiding, motor bearings are getting a hiding, and eventually it will destroy itself. If we look at that calculation as to whether or not a pump will pull water from below the ground, and this is an application where we're pulling cold water. We're pulling water from a stream and we want to pump it out. We must make sure that atmospheric pressure, which is the net positive suction head available, is always greater than the net positive suction head required. And on the pump curve up the top, you can just see we've got our performance curve, we've got our hydraulic efficiency curve. In the next box down, we've got our power curve. And the next one down is the net positive suction head required. And the pump manufacturer must give you that curve. That indicates the net positive suction head required at that given flow rate. So where the red dot is, our flow rate is 70 cubic meters an hour on the pump curve. If I drop my eye straight down, I hit the net positive suction head curve, and that tells me that the requirement is 3 meters. So at that duty point, my net positive suction head required is 3 meters. So going to the calculation, we have our net positive suction head available, which is atmospheric pressure. And I always work on 10 meters, even though it's slightly greater. So you're starting off with 10 meters. From that point, we have to take off the suction lift, which is, as we know, from the water level sitting in the well to the center line of the pump. So we take off the suction lift. We have to take off the friction loss from the foot valve and the pipework. Then we also have to take off the vapor pressure, and the vapor pressure chart is down the bottom there. For 20-degree water, it's not a lot, it's about 0.24. So we take that calculation, and that gives us the net positive suction head available at the pump. As long as your calculation of your net positive suction head available is greater than the net positive suction head required, which is 3 meters, then that pump will work. If you don't have that, then it won't work. It'll cavitate. One thing to be aware of is always consider if at some stage that pump may shift along the curve, because if that pump moved from 70 cubes to 80 cubes, then your net positive suction head requirement has just shifted up to just over 4 meters, and that could be the difference. You could then have a greater net positive suction head required than your net positive suction head available, and then the pump just won't work. When we work with higher temperatures, let's say we're working with 90-degree water, you can see now that the vapor pressure is 7.41, which is a lot higher than 20 degrees. So if our vapor pressure is 7.4, that only leaves us 3 meters off our net positive suction head available. So the likelihood of you being able to lift water at 90 degrees is pretty low. Your pump would have to be pretty close to the water level, and all your losses would be quite low. The other side of the coin is if you were having if you were going to a steam boiler house. If you ever go to a steam boiler house and you'll see a pump pumping water into the steam boiler, the condensate tank which feeds the boiler feed pump is always mounted up in the air. So now we have got a flooded suction. So the water, so we take our net positive suction head, which is atmospheric pressure at 10 meters. On top of that, we add the height of the tank, which might be 2 meters. So now we're starting with 12 meters. And when you have 12 meters, that means that 90-degree water is quite possible. And we can pump water at 90 degrees. And that's the case of the steam boiler. They'll be pumping water around 90 degrees. So they need a much higher head to overcome the vapor pressure, the friction losses, and then the net positive suction head required for the pump. When it comes to centrifugal pumps energy use, the first thing we need to understand is, do we actually need a variable speed? Most of our schedules and specifications now have variable speed. If you don't need a variable speed, if it's not giving us anything, then there's no real need for it. To be fair, variable speed costs have come down hugely over the years, so it's made it a bit easier. If we're not too sure what our pump head's going to be or what our flow rate, then perfect VSD is ideal, because we can just adjust the speed of the pump to match the flow that we're looking for. So we might be in a system where we're trying to get some flow through a heat exchanger or whatever. We can just adjust the speed manually to get it to where we need it to be. In larger systems, as in water boosting and heating and chill water, is it a good idea to have one pump? Probably not necessarily at all, because as we know now, we try to run the pump in a good area on its performance curve around that best efficiency point. And if you've got a large pump which has a peak of, say, 30, 40, 50 litres a second, but then most of the time it could be running at 10 litres a second, then it's a good idea to split that into 2 pumps or 3 pumps to manage it much better. So as we put in more pumps, then we have a better efficiency, because each pump has its own efficiency, and we can drive that pump to a better point, and then we can save some energy costs. And here you can see this is a multi-stage pump. Has a nice steep curve, but no different concept to the variable speed. Now we have multiple curves. The fixed speed pump would be the 100% pump curve. The other curves are between 25 and 100%. And looking at the 2 dots, what we've got here now is we've got a pump running at around about 6.5 cubic meters an hour, and it's producing about 35 meters head, and that would be the peak load. But at minimum demands, it's only looking for 1 cubic meter an hour. So we can actually slow the pump down, maintaining a constant pressure. Instead of driving high up on the curve to the red point, we're actually flatlining. We're maintaining the same pressure and we're producing a lower speed. We've actually dropped our speed to about 80%. If you drop your eye down to the second box below here, you can now see at our peak load where we were doing 6.5 litres a second, we were using about 1.3 kilowatt. If we had a fixed speed pump and we were running up on that high performance curve where the red dot is at the top, we would be drawing about 0.75 kilowatt. But now we're using the VSD and we're following that flat line with the yellow dot. We've dropped our power consumption to 0.43 kilowatt. And we know that when we're running on a pump on a system, unless it's a cooling tower or a fixed duty, generally we only run that pump for a very, very short time on the peak load. If I just take you back, and you can see here how the system might be working. So at the peak load, for a very, very short time, but most of the time your hours are sitting spread down on low loads, and this is where the VSD and the energy savings can be huge. Come back to us to help us out. It gives us a lot more system control. It's easier on the system, and obviously a lot less energy. We can look at some different types of control modes. Constant curve, that's the one there we can actually just manually adjust the speed of the pump. So you can say to the pump, okay, I'm just going to manually drop you from 100% down to 85%. And then if I've got the right flow and head in the system, and then I'm happy, it's all go. Constant pressure, which is the guy below. We use a lot of constant pressure in water boosting. Constant pressure also in heating and chilled water where the systems are not too large, but there's not a lot of pipe work. If the pipe work runs along, then we can use proportional pressure. Why we would use constant pressure in smaller runs is because of the valve authority. This way here, when using constant pressure, we're still maintaining a good pressure, but we're still reducing the pump speed to match the demand. If we go to proportional pressure to the right, you can see now, as I reduce the speed, I drop my head and I drop the flow rate at the same time. So we are now pulling our energy down even lower because that pump's running 190, 80, 70, about 65%. So that's quite a bit of energy pulled down. And then temperature control, we're able to actually reduce the temperature way down. And this is typical of a domestic hot water loop. And you've got a return main or a ring coming back, putting a small pump on the return leg and VSD it and run it on temperature. And you can see that at low loads, when there's no demand, it's running like a light bulb. There's not a lot of energy at all coming from that. The next part of the section is on some new developments and things that have been happening in the last couple of years and moving on. For pumps, I guess the changes have been huge, and I've seen a lot more changes in the last 5 years, 10 years than probably before that. But way back when you look at the original old pumps, like this one here, this is a sales thing now, but that's a Grundfos, one of the first water pumps called the Pig. Very, very basic, had a pump, had a motor, and that was it. That's all you got. Nowadays, there's all the bells and whistles. There's flow balancing, it's self-commissioning, it's wireless. 2 pumps or 4 pumps will talk to each other without a control panel. You've got all the sensors integrated. You can even use your mobile phone to talk to the pump for commissioning. And to the point for the guys that are commissioning pumps these days, you can draw up the pump curve. You can dial up the pump curve on the display, and it'll show you where the pump's running, the head, the temperature, the water, the power. So much has changed to make life so much easier. More and more is going into the pump as a package. It's almost becoming its own little PLC BMS, and more accepted. The efficiency we mentioned before in Europe under the EUP directive, which Grundfos and a number of other European, Wheelhouse, Metegard manufacturers we must meet this directive that was brought in a few years ago for the hydraulic efficiency. They take a measure, and what they do is they'll take the peak efficiency, the best efficiency point, 75% of the best efficiency and 110, and they'll make a calculation, and that comes up to a figure, and it was 0.1. The EUP directive was to change that in 2015 to 0.4. What it did was take that efficiency, the shape of that efficiency, it's still holding the same peak, but it broadens the peak. So now we've got a pump that can work under variable loads and still maintain a nice efficiency. Whereas if you take an efficiency like the grayed out one, which is very peak, it's all very well to have your pump running at that efficiency, but as soon as you drop the flow rate 20, 30%, you've just run out of your peak efficiency, and now it's costing you money to run that pump. So in doing this, it's reduced the energy, and the pump's going to run a lot smoother. The target is 0.7. So the MEI target is 0.7, and most manufacturers now will meet 0.7. So for the customer, it's a real bonus. It's a real benefit. That pump is going to be running a lot smoother. It's less service and a lot more efficient over a broader period. The bulk of our systems now are variable loads that we don't generally run as a fixed speed or as a on a 3-port valve. Motor efficiencies, the EUP directive for motors is for some time now has been IE3. We have an efficiency standard here, efficiency 1, efficiency 2. Looking at the European one, they have an IE standard, and efficiency 1 is equal to their IE2, whereas their standard minimum motor requirements are IE3. Motors now, we have out with IE5 motors. IE5 motor is 10% more efficient than an IE3. Energy savings are just quite huge. And you can see by the graph down the bottom, it's not so much up on the peak where we've got a big change, because they're all very similar in that point, but it's when we're actually pulling to the left is where we're starting to see a bigger gap between the efficiencies, and this is where we're running our pumps and motors a lot at those points. Improved system control, and we've all seen it over the years. We used to have, and we still use 3-port valves in certain applications because we need them, but as time's gone on, we've moved to 2-port control, and in 2-port control we now vary the speed of the pump to match the system, whereas when we use a 3-port valve on the top there, the pump doesn't know any difference. It's designed to push the water through the 3-port valve into the unit that it's supplying to, or if the valve moves, it'll actually just send it back to where it came from. So the pump just carries on, not knowing any different. Whereas the 2-port valve, as the modulating valve is starting to pull down, we can reduce the speed to match the system demand. Here we have a couple of circuits, and the top one here is a variable flow system, primary only. So the primary pump, it requires a certain pressure drop, as you can see it below the buffer tank here, to get the water through the whole system. It's got to feed the water through the tank out into the pipe work to each unit. It's got to get it through there and then back in again. So that pump has to produce a reasonably high pressure to get it through to that system. And then the valves will be modulating at each unit and on the coils. Whereas the variable flow system below is very good for pump sales because there's more pumps, but there is a bonus. There's some energy savings and better control. You can see now at the buffer tank, the pressure that's required for the primary pump is a lot lower. The primary pump is only pushing the water through the loop, and then at each air handler or fan coil, we've got individual pumps that are actually managing those by themselves, and so they're much smaller. All they're doing is drawing water off that primary loop, and they controlling themselves more individually. So as each one of these units changes, that pump can change with it. It's not just one big pump having to try and manage all the little pumps at the same time. It's another system which they've been now using in Asia and Europe. In this particular case, they have do away with the valves, and again, this is going back to pumps now with controls and extra inputs and outputs that are available. In this particular case, we take out the modulating valve and we take out the balancing valve. The modulating valve would have been getting a signal from a duct or temperature sensor or from the BMS to open and close. That signal now has been sent into the air handler pump. So that air handler pump now replaces the valve. Inside the pump, you set the maximum flow rate, so that's your balancing. All you need to do now is put a check valve on each air handler, set the pump to the flow rate that is required, and then away you go from there. You'll notice between the two of them again, it's gone from a primary to a primary and tertiary pump. And the first one on the left-hand side is one pump only, a primary pump. It has to feed through every piece of that pipework in every part of that unit. Whereas now, on the second one here on the right, you've got the small primary pump. All he's doing is feeding water through that loop, through that chiller, through that little bottom end loop. The little pumps are drawing off that. So each one of those is individually sized. This, on the right-hand side, the blue box here, this was a job done at the Ngee Ann University in Singapore, and they had nearly 55% energy savings. Then they had to change their primary pump because it was oversized. We're moving along quite well. This is the getting on to the last section, and this is quite interesting. I find this interesting and quite helpful when talking to contractors. The installation and the piping fundamentals, it's really important. The pump, I guess, is just not a pump anymore. It's part of the system. It's part of the package. And if we're looking at trying to save energy, the best way to do it is to make sure whatever we're putting in there can do its best. With the pump struggling, if it's starving, it's not going to perform. It's going to be inefficient. So we need to make sure that the suction piping and or if the water supply coming to the pump is correctly sized. If we have restrictions in the pipework and bends and valves and bits and pieces, then the pump's going to be noisy during operate. It's going to vibrate. It can possibly cavitate. Again, premature failure, mechanical seals and motor bearings. We like to have a laminar flow entering into the pump where you can see the water's nice and smooth and it's entering in, because it's got to get into the impeller of the pump and then it's got to get itself out of there again. If the water coming into the pump is turbulent, it's going to hit that impeller, it's going to be noisy, it's going to transfer that vibration down the shaft into the motor bearings and into the mechanical seals. And over a period of time, we're going to have to get in there and service it. So we need to have 5 to 10 pipe diameters of straight pipe coming into the pump. So if it's a 100 mil connection, we want 500 to a meter of straight pipe. That way, when the pipe enters, the water enters into the pump, it's nice and smooth. The pump can take that water and discharge it out, and it's quite happy. If we can't, if you cannot do that, then we put suction diffusers, and we can mount those onto the inlet of the pump. And a suction diffuser is basically a 90-degree bend, and it takes out the turbulent water and causes it to be nice and laminar going into the pump, and it works quite happily in that way. So valving, we need to have those set back from the pump. Again, it's a huge turbulence. Strainers, we like to keep those away from the pump as well. And also remember, if the strainer's on the suction part of the pump, it will get blocked, and there's a possibility that the screen will block and that could starve the pump. And the diagram at the bottom there is actually showing a 90-degree bend, and you can see what's actually going on. It's forcing the water down. It's pushing the water onto the pump, and trying to force the impeller down. Again, it's just stressing right down through to the rest of the motor. Reducers, if it's a horizontal pipe running along into a pump, always use an eccentric reducer. That way, if there's any air in the water, any entrapped air, which there will be entrapped air, it can actually pass through the pump and out again. If we use a concentric reducer in a horizontal pipe, then you've got a good chance that you're going to get entrapped air caught up. And if it's bad enough, if we lose our system pressure, then it'll accumulate, it'll cause noises, it'll starve the pump, and a number of other issues. Avoid high spots. I remember going to a building in Wellington, and they said, "Oh, your pump won't run, we can't get it to run." And I climbed up into the ceiling to have a look, and it was a big U shape like this, and they had the pump sitting in the leg. Somebody had been in and serviced a radiator down the bottom, and they bled the system, but they couldn't bleed this point because there was an airlock, and the pump was just running, but there was nothing happening. Another one was at a hospital, and it had a number of water supply tanks, and it had a 300 mil line running off the tanks across the ground. They'd put a nib wall around the tanks, so they had a big hook like that over the top of the nib wall, and away it went. And that would accumulate air sitting in the top of that point there, and the pumps were starving. And once we cracked it and got the air out, then we understood that's where the problem was. Because you're always going to have air in the water. We can't do anything about it. If we change the temperature or change the pressure, that entrained air will come out. Another example was a water supply line, and it was on a farm, a long alkathene line running across a paddock into a spring. They had a jet pump, so the jet pump was actually drawing water from the stream, running across the paddock into the eye of the pump, and then being pushed up into a tank. In the morning, the pump would work as good as gold, but as the day got on and it got warmer, the pump would stop, it would starve, it lost its prime. What was happening was the alkathene was heating up, and that water was giving off the entrained air, and the air was actually accumulating, and it would just airlock the pipe. So we try to avoid all these things as much as we possibly can to make life a bit easier on our system. The chart up here is a really good chart. It's from Spirovent, and you can see here that at 3 bar at 20 degrees, we've got 73 litres of air per cubic metre. If we lost our pressure tank, let's say it's a heating system, and our pressure tank in the basement, we lost that pressure to 1 bar, we've just given off 35 litres of air into our system. And that air circulates around, it accumulates to the point where it can actually airlock, and you won't get heat into the radiators, you won't get heat out, it will airlock the pipework, and eventually it'll get into the pump at the same time. So as we decrease pressure, the temperature, the air will come out. If we increase the temperature on the same time and we don't have enough pressure on the system, then we'll get that air out of there as well. When we talk about cavitation, a good way of testing a pump to see if it's cavitating is to get the valve after the pump and pull it back, just close it off. And if that noise goes away, then you know it's cavitation. Because what you're doing is, you remember going back to that pump curve when you saw that MPSH requirement curve. When you grab that valve and you actually shut it off, you reduce the flow, you're dropping the MPSH requirement, and you're getting back to a balance where the atmospheric pressure is greater than the net positive suction required, so the cavitation goes away. If the noise doesn't go away, it can be air entrapment, because they sound very similar, but the air entrapment won't do as much damage as the cavitation will. That's for sure. Other places where we can get air, we're pulling water out of a stream, a cooling tower,
If that water level is 500, less than 500 mil, then you can pull a vortex from the surface. So you'll get air pulling down off the surface, like pulling the plug out of the bath, and it'll draw it into the intake of the pump, and it'll cause the pump to starve, and eventually it'll stop pumping. We can get the second diagram down. You can see here's a lot of aerated water coming in here, and that's going straight into the pump. To overcome both those, we can put baffles in. So the top diagram, you would put a baffle on the water, and the baffle would be much wider than the diameter of your intake pipe and stick out quite some distance. That way, the vortex can't be pulled down from the surface. It can only draw the water from around the intake. The second box, what we can do there is like we have on the bottom, is put a vertical baffle in. So now the water is entering into the stream, into the water. The discharge pipe into here is a lower, and the air bubbles can actually come up and then escape the atmosphere, and then the water is pulled across into the next pit, and then it is pulled away from there. Pumps on foundations and bases. When we pull a pump down, it's got to be secured hard down to the foundation. It's got to be flat, nice and level and flat. If that foundation has got any humps or bumps in it, what you're going to do is when you pull the pump base down, you can distort it, or you can put pressure on different corners, and that then is going to load onto the pump and the motor. So then eventually you're going to start to get some wearing in the bearings, or you're going to get impeller rubbing on the pump housing. If you're going to put vibration spring mounts underneath a pump, never put it under the pump base. This mounts must go underneath the inertia base. When you mount a pump onto the foundation, like the top drawing here, that might be a pump, that's a basement. And if you've got a basement and there's nothing underneath it, there's no reason why you can't put that pump on its steel base and pull it hard down onto the concrete. As long as the mass of that concrete is 1.5 times the mass of the pump and the motor, it'll all work fine. And then the vibration will go into the foundation. It'll be absorbed into the foundation. If, however, you're placing that pump in a room above an office area or above an area, you don't want any vibration to move down. This is where we'll bring in a inertia base. Just a rule there too, or just something to think about. When you pour your foundation, like you've done in the top box here, and you're going to mount the pump, make sure that the foundation is at least 100 mil larger all the way around. If you mount that steel base onto a concrete foundation and it's not wide enough, and those bolts can actually, where you fasten the steel base to the concrete, can break away, and it'll chip that concrete away. It'll set up vibration, and it'll destroy itself. We had a motor, a 90 kilowatt motor. It did that. One of the back end securing down bolts wasn't there, and within 3 months the motor bearings were frozen onto the shaft. They had to gas cut the bearings off. So vibration will really take off. One other point while I'm thinking about it as well is when you're starting up a pump, you're commissioning that pump, always get the discharge valve and close it off. So when you start that pump, just open the valve slightly and hold it there. You're holding the pump high up on the pump curve. When the system is filling and it's balanced, then gradually open up the valve. What you're doing is you're holding the pump high on the curve and you're giving it some back pressure, you're stabilizing it. When the system's filling and moving, you've got air moving around in the systems, the pump is running up and down the curve. It's bouncing backwards and forwards. And that's just putting a lot of stress back onto the pump, onto the mechanical seals. So when you start up a new system or start up a new pump, any pump, get the discharge valve, close it off, and just crack it open slightly, run the pump, let it settle, and then open up the valve and let it go from there. We're getting now to the last part of the slide. So this is a full blown pump on an inertia base. Remember, if the foundation is solid enough and there's nobody underneath it, mount the pump and the base directly onto that concrete pad and pull it down hard, and it'll be as good as gold. However, if there's something under the floor that we don't want to transfer any vibration down into, then we must put an inertia base on here. The inertia base is a concrete pad, which is 1.5 times the mass of the pump and the motor. We then put vibration dampeners underneath that. So now, if there's any vibration, it goes into the concrete pad. It doesn't get transferred back up into the pump and the motor, and it doesn't get pushed past the dampeners. And this will lock that vibration in on that system quite happily. One other job we had, it was a little pump, and the engineer thought he'd do a good job, and it was a vertical pipe running up a wall, and it was underneath a doctor's office. And the pumps were sitting in the vertical pipe with the motors hanging out. They're only small, but he thought, oh, I better safeguard the motors, so he pinned them to the ceiling. And even though the pumps were small, the doctor was in his office one day, and he put his pen on the table, and he watched it roll off the edge of the table, and he couldn't work it out. It was just a very small motor, but because the way it had been installed, it set up vibration through the ceiling, enough to upset his pen. So vibration can be a real pain in the butt. This is why in cases where we don't want vibration being transferred down, we use an inertia base and the vibration mounts. When we use the mounts, make sure that they're sized correctly and make sure that we don't get them mixed up. All the vibration mounts come at different spring levels, different weight loads. If we get them incorrect, then we can get the pump tipping. And again, you'll have issues in here. Most of these motors are IP55, fixed speed motors, variable speed motors, whatever. If we're going to mount them outside, please make sure that we put a small cover over, just a little hat over the motors, and that prevents the driving rain and the condensation. Where we get days, it's a beautiful day, and 3 o'clock, 4 o'clock, we get a bit of condensation. That condensation gets into the warm terminal boxes of the motors, and it will eventually destroy it. So just a small cover, it doesn't have to be huge, just enough to stop that driving rain and the sun, and stopping the condensation that's getting caused in here. So that's that's the last slide, and I'll hand that back now, and then we'll go from there. So, but thank you very, very much. I hope it was been of interest, and more than happy to help you with any questions. Thank you.